Alright, another draft physics video presentation. Alright, we're going to start with a Veritasium video that's just all, I don't know what to say. It's very complex. Bunch of stuff you have to accept as being true. It's not consistent with any theory. It's just, it's fixed with dark matter. It's this whole lensing thing and they throw in the time dilation and a whole bunch of other stuff, and it's a mess. And so I'll just point out the, just obvious criticisms, but obviously there's just you don't get any critiques. I mean, it's like none of this has to be reviewed by common sense or rationality, or there's just nobody fact checking any of it, so they can just say anything and get away with it, and it's just such nonsense. So we'll start there. And then he leaves a citation to a guy who he consulted with for this video. And that was the more interesting channel, kind of. But anyway, so we'll go there, talk about fields eventually. And that'll get to the point of how this is all really simple, and they're just made such a mess out of physics. So I'll play some of this hype.
Essential components: the source, the lens, and the telescope. If the lens and the source are spherically symmetric, and
so he just said if they're spherically symmetric, so obviously the gravity would be the same, by the distance rules. So that doesn't even make sense because galaxies aren't shaped round. Galaxies aren't symmetric in that sense. There's more mass on some levels, and there's less mass in other levels. So they wouldn't be symmetric.
The source, lens, and telescope are perfectly aligned.
Then we say alignment is required for this event to take place, and then they say later he'll say something exactly the opposite, in the sense he'll say we can see the source at the same time as we can see the lensed objects. It doesn't make any sense. I mean, the source would be, somewhere above. I have to make an arrow that I can move around. I have to do that. I forgot to do it.
You get what's known as an Einstein ring. The light.
Right, all right, so let's understand. They called it an Einstein ring. Einstein predicted it would be infinitesimally thin because the gravity's just not going to work this way. It's going to give you one place in the gravitational field where the lens will be the right strength to bend the light. Because Einstein knew that gravity lenses wouldn't be able to convey whole images because they won't be what a lens needs to be. They won't even come close. And the fact that the path length differences are so dramatic, you're not even looking at the same object, frankly. The different photons are traveling such different path lengths that you can't be watching the same thing, the same event. So you wouldn't see anything that has a size. So if I tried to lens this piece of chalk, only one tiny shred of the chalk would be able to be lensed. That's Einstein's theory. So again, they call it Einstein's ring, and no, Einstein didn't predict anything like that. He predicted it'd be so thin a ring you wouldn't see it. That's the actual prediction. So they don't even tell the truth, okay, that Einstein wouldn't go for this. Because Einstein did draw it on a piece of paper probably and figure out it just doesn't work. I can't make a gravity lens create a true image. It's just not going to be able to do it. It's going to bend some light too much and some light too little. So depending on where the photon comes from, the path lengths will be different. I won't even be seeing the same time. Some of the light's going to be from a different time than the other light, because a gravity lens, unlike a glass lens, it isn't going to compensate for the speed difference. I mean, for the difference in the, obviously the vector's going out for light to be refracted, and bent towards your eye. The light on the outside travels a lot further than light on the inside. And the trick is a glass lens slows light down, blah, blah, blah. So it slows it down for the shorter path, and there's less slowing down for the longer path, and therefore the two compensate and you end up seeing both images. All the photons are of the same time because you compensate essentially for the time difference. These lenses are huge in space, hundreds, thousands of light years of spread. Obviously the path lengths are insanely different. You're looking at, one photon would be, you know, 100,000 years before the other photon. Obviously, the object couldn't be in the same position for 100,000 years. I mean, these are obvious, glaring flaws in this theory.
From the source is bent around the lens equally in all directions, leading to the image of a smeared out ring.
So again, none of these are ever symmetrical. They don't make any mathematical sense. This overlap, none of this makes any sense. That's not spherical gravity. It's certainly not consistent gravity. And again, you're seeing all of these image details, all of these galactic image details, little stars, little bright bits, all of this stuff. You'd never be able to get any of those coherent images. You'd never see them as they are. You would see perverse and complete distortions. You would never be able to recognize the image.
If the source and the lens are spherically symmetric but are not perfectly aligned, then what we end up seeing is a break in the Einstein ring. It splits into two semicircles.
Right, so it's not spherical gravity, it's lopsided gravity. And again, then you have to have exactly the right amount of bending. It has to be just perfect coincidence or something. Because again, the path lengths are completely different, and therefore the time is wrong, everything's wrong. The stuff can't be in the same place. We're talking hundreds of thousands of years of difference in when the photon left. How could it leave from the same location? It's not possible.
And if the source, lens, and telescope are aligned, but the lens is not axially symmetric, for example, it could have an elliptical shape.
So again, we've changed the rules. It's not symmetric. Yeah, exactly.
Then you get four images in the shape of a cross.
Yeah, well, so they're saying it's lopsided. That is, bowed this way and bowed the same way this way. So that somehow gives them an excuse to say, well, the distances aren't symmetrical, between the crossbar and the long bar. They're not the same length. So they're just finding an excuse to say it's an Einstein ring, but it's a funny shape. And again, the funny shape would mean hundreds of thousands of years millions of years of difference. And so how in a million years does the object not move in space? Theoretical impossibility.
An Einstein cross. So what happened with our supernova is 9.3 billion years ago, a dying star in a galaxy
So 9.3 billion years ago.
far, far away went out with a bang as a supernova. The explosion sent out a blast of light in all directions. About 5 billion years ago, before the Earth even existed, that light encountered a very massive object that warped space-time.
Right, but that light didn't encounter that giant thing at the same time. Some of the light got there billions of years ahead of the other light because it's traveling a different vector. You can't magnify without creating different vectors, right? This is the whole point. And again, it's not the same. It's nothing like glass slows light down, 40%, a huge amount, to be able to do this compensating. There's no evidence that gravity has any such effect. Anything nearly substantial enough, a change in the time it takes the light to travel, that would ever compensate for the time differences of where the light came from.
It was a cluster of galaxies called MACS J1149.5 plus 2.
What a waste of time.
223. Yeah, I know that's a mouthful, but the name just tells us where in the sky it was discovered by the Massive Cluster Survey.
Whatever. It's discovered. It was discovered. Oh, you mean it was just photographed? Okay.
This galaxy cluster is made up of lots of massive substructures, like individual galaxies and halos of dark matter. At some point...
So, halos of dark matter, we have to accept the existence of that. So, of course, that's how they erase all these mathematical problems, is to pretend there's a bunch of this dark matter there, and it creates all this fake gravity. So you have to believe all that crap to believe any of this.
As the light traveled through this region, it encountered an elliptical galaxy almost perfectly lined up with where the Earth would eventually be.
Right, so he just said it encountered this galaxy, and this is actually the one it encountered, right? I mean, the host. This is actually the host right next to it here. So the light went over here, came in here, and then went to the Earth. I mean, it doesn't make any sense. This image is actually the image. This is supposed to be the host galaxy, the one above his arrow, the little one with that little blue dots in it. That's supposed to be the host galaxy. The lensing galaxy is supposed to be that stupid blob. What sense does this make? Oh, that's right, 0 cents.
And the gravitational deflection focused light rays that were initially diverging onto paths that converged at the Earth. This is why.
So this silly drawing doesn't make any sense at all. So he's showing light diverging on this cluster, and then he's showing light being bent way out here that gets to the Earth, and then he shows lines that don't get to the Earth. Not a very useful diagram, because of course this requires, because of the inconsistencies, these paths have to be very different.
We saw the same supernova in 4 different locations.
Okay, so and just look where just see where the locations happen to be, right? You can see it right there in that image. Okay, the little yellow dots are supposed to be the same thing, and they just happen to be lensed right in the path of the spiral arms of this galaxy. That's a coincidence. I mean, these the two things don't have anything to do with each other. The little bright thing isn't supposed to be the thing doing the lensing, frankly. But I mean, isn't that awful convenient that they just happen to lens right in the spiral arms of the galaxy? That of all the places they could lens, they just happen to lens where there's other objects. See, they're not really there. They're in some other galaxy. So just understand, they're not really there. But they just happen to lens right in the spiral arms of this other galaxy. And as you can see from these two pictures, right, one galaxy is obviously... These are two galaxies that are interacting with each other. They're in the same place in time, right? You can sort of see one galaxy sort of eating the arms of the other galaxy. So none of this makes any sense.
Not only did the supernova appear at 4 different places, the images also appeared at different times. Relative to the first image, the others were delayed by periods ranging from 5 days to over 3 weeks.
Right, 3 weeks is nothing, right? We're talking about photons that would have a delay that would be, again, hundreds of thousands, millions of years difference in the photons. No chance that they're a few days different. No chance.
And we could measure this time delay because of the distinctive light curve of the supernova. Some of the images of the explosion were further along in their light curve.
Yeah, see, the light curve just means how bright is the little dot, right? But the images don't show any of that. They only have 4 or 5 images. They can't see any of that. It all looks like they showed up at the same time and they all left at the same time. Well, we don't even have the left picture, by the way.
Than others. This was a particularly lucky discovery. It's the first time a multiply lensed supernova has ever been observed.
Yeah, it's the first time. Yeah, anybody said that's what something is, right? So it's not the first time probably, but it's the first time somebody said it and you believed it.
There are other objects that, due to gravitational lensing, appear.
And everybody buys this crap too. Again, no spherical symmetry. You got swirly line here, swirly line here, swirly line here. They're not in any way geometrically in the right places. They're not in the right shape. It doesn't make any sense at all. Mathematically, it fails.
Multiple times on the sky, like multiple images of galaxies, but these objects don't change predictably with time, so there's no way to use their images to work out the relative time delay between them.
Yes, and a matter of days isn't going to do any good either. So the supernova changing over a 30-day period isn't going to help you any.
Now, one reason for the time delay between the supernova images is because
So again, they have the source billions of light years away from the other galaxy. So you saw that the two galaxies looked completely tied to each other. One was consuming the other one. It seems kind of obvious, but they're actually saying they're 5 billion light years away from each other in distance. Implausible.
paths the light took were different lengths.
So he does the same crappy image that doesn't mean anything. Again, he has lines that aren't symmetrical going in, and then he has these lines symmetrical. I mean, what, sorry, you can't see the mouse. I have to fix that, I guess. I have to have an arrow, because unfortunately the mouse never records the right position.
Just took the light longer to travel further. But there is another reason, which is that light passing through curved spacetime appears to travel more slowly relative to an external observer.
Yeah, and it's an insanely small amount, and blah, 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 and obviously it can be just blamed on scatter again.
This is much less intuitive, but it's a well-established and well-tested part of general relativity.
No, it isn't.
Back in 1964, Erwin Shapiro suggested it would be possible to test this gravitational time delay by sending radar signals to Venus and measuring how long it takes for the echo to come back.
Right, so all these experiments go right through the corona of the sun. Obviously, there would be a time delay going through the corona of the sun. Duh. So, I mean, not even interesting.
He calculated that due to the gravitational influence of the sun, the signals would take an extra 200 microseconds when Venus was on the other side of the sun compared to when it was close to us. This is solely a gravitational time delay, not related to the extra distance the light has to travel.
Yeah, right. Sure.
And within a couple years, experimental data revealed the gravitational time delay for light traveling past the sun was exactly as predicted.
Right, and it's exactly can be blamed on scatter.
Today, in order to accurately determine the distance to the Voyager and Pioneer spacecraft, this Shapiro time delay must be taken into account.
Says you, and we don't have any evidence of that, and we don't have any evidence it's a meaningful delay or anything else. And obviously there is stuff in the universe, and light has to travel through stuff. It takes time to travel through stuff.
Now I want you to have a look at the 4 supernova images again.
Right, silly. Okay, so again, it's a pretty good image. You can sort of see these two items, the two objects that are next to each other are obviously interacting with each other. Now, they're saying they're not. They're saying one of them is 5 billion light years away from the other. No, I don't think so.
Do you notice how the same galaxy appears 3 times in this image?
Right, now does that make any sense? And different, completely different sizes and in different orientations. So again, just throw Einstein out the window because he didn't know what he was talking about. We can lens entire objects and it'll all be in perfect order and all the little stars will be in the right place because all the paths are the same distance for some irrational, insane reason. And even though the gravity lens is exactly the opposite of magnifying lens, even though there's no reason to believe it's in any way a shape that consistently magnifies at any distance, it would have to be very, very specific distances. This is just bullshit. 3 images. Obviously, there's something wrong with your camera if you're getting 3 images. So again, these are highly processed images, so who knows what their filter is doing, but it doesn't make any sense.
That is the supernova's host galaxy. It is itself lensed by the massive galaxy.
Right, so he just said that's the host galaxy. Did you hear those words? So somehow in the same image, something is supposed to be behind something to be lensed. So the image he showed us was the object was behind. That's why we have the Einstein cross of the 4 images. No, it doesn't have to be behind it. We just made that part up. It doesn't mean anything. Forget the being behind part. No, you can do this, go this way and then go this way. You can do really sharp angles.
Cluster MACSJ1149.5 plus 2223. In fact, this cluster lenses tens of galaxies. So scientists had been studying and modeling the distribution of matter in the cluster long before the supernova. They asked, if we see these 4 images of the supernova in one image of it...
Yeah, so this was the silly part, right? So they're saying that these lensed images, the guys saw these lensed images and then said, well, let's look at the real galaxy and we'll be able to see the supernova. Well, how could you see it? The lensed images have to be a longer path length. They have to be longer path lengths. They can't be a straight line. And now you're going to go look at the straight line and somehow the straight line is going to happen in the future. So the shorter distance the photons have to travel somehow is going to happen in the future? It doesn't make any sense.
This host galaxy, when would the supernova appear in these other 2 images of the host galaxy? And using the models of mass distribution and general relativity, they calculated that in this image, the supernova would have appeared 20 years earlier, in 1995.
Right. So this is the what? No.
Now there are no close-up pictures of this part of the sky from 1995, so there is no way to check. But in the other image of the galaxy, they predicted the supernova would appear again in about 1 year's time, almost exactly when it showed up in that Hubble image. This successful prediction...
So, yeah, that little thing in the circle, you can't even see it, blah, blah, blah. So all the other images, you see everything, you can't see shit, but whatever.
...is a fantastic confirmation of our understanding of light and gravity on the scale of the whole universe. But it has even bigger implications. One of the hottest debates in astronomy right now...
Okay, well, forget that part. So I'll just show some of the images. I mean, I went looking, and this one doesn't tell you much. Well, here, this is the host galaxy, and here's the lensed image. So obviously they've created an Einstein ring without the host galaxy being actually behind the thing. Because they're saying this host galaxy that you're seeing here isn't really a galaxy. It doesn't really exist there. It's someplace else. This is actually another lensed image. And well, you can see that these two things are obviously connected to each other. The two objects are obviously interacting with each other. I mean, and so again, we're supposed to believe it's just a coincidence. All right, so this is the the part to understand. It's just a coincidence that these little dots just happen to be right on the spiral arms. That's just a coincidence. That the dots happen to be right on those spiral arms. The same spiral arms that have little dull blobs in them in the previous picture, indicating something else being around. But it just happens that the lensed images, the four fake images, the four illusion images, just happen to show up right on those arms. Just a coincidence. Alright, crap. I mean, just so frickin' stupid. Alright, so let's move on to this stuff, which would be a better subject. So there's lots of physical problems. I mean, this is like the LIGO thing. No one goes through this thing and starts talking about how can you measure 1/10,000th of the width of a proton, in beams of light, that you're sending through mirrors 1,600 times. How can a mirror possibly be so reliable and where it reflects a photon? I mean, it's just nonsense. Anyway, so this is one of these guys was apparently a consultant for the Veritasium wacky lensing stuff. So they're both cosmologists, and they're going to talk about fields. And so I just thought this would be a door opener for me to just point out it's so much simpler.
So we're back, and I think it's time to talk a bit of, say, fundamental physics, the things that we have to deal with when we want to learn something about the universe. And so this is essentially related possibly to a viewer's question, but when you get to university, you start talking about various things, and then there's this concept of a field.
Mm-hmm.
What is a field?
What is a field? Well, so let's just roll back in time. So when you turn up at physics, the first thing they start teaching you is Newton's ideas about the universe. And for Newton, it's just all particles. And so here's a theory about how particles move around under forces from other particles.
It's about forces in the sense of it's about push. It's about things forcing things, hitting things. So in that sense, Newton figured out the obvious, that stuff moves because something hits it. And, you want a counter force, then you hit it going the opposite way. I mean, it's kind of obvious stuff. You push it with this finger, and then you push it in the opposite direction with that finger, and it stops. Not too complicated.
And even gravity, there's no real sort of field there. That's not an idea that's there for him. It's a spooky action at a distance, but it works. So
that's nothing like Newton, right? So Newton clearly stated, he didn't know what it was, but he knew it was something. Okay, and he clearly pointed out that no reasonable person thinks that it's just happens instantaneously. It just poof, it happens. That there's obviously something causing it. So he was very interested in the fact of what the cause would be. He just couldn't say what the cause was. I mean, these people just don't care about the history at all.
So that'll work.
So for Newton, you have two masses,
Yep.
and you ask how does one mass influence the other mass, and you talk about the force between them.
Mm-hmm.
So this mass produces a force on that mass, this mass produces a force on that mass, and then things do their things.
Yep.
Right, and the force looks like it's just a straight line force heading right for the center of the Earth, okay? So something has velocity in a direction, and it appears, by Newton's figuring, there's something acting on it, a force, and it pushes it into the Earth, so to speak. Okay, so there's something that compels it to move towards the Earth, and the compulsion appears to be something heading right for the Earth. And again, Newton had been aware of Faddeo's theory, blah, 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 and obviously there was a lot to consider in terms of they didn't know what the elemental universe was made out of, so they couldn't really talk about the speed of the force. But again, there's every indication that Newton had already, opened the door to the fact that he doesn't know.
According to his equations of motion. So you can use F equals ma. You can calculate what happens to the masses.
Yeah.
So what's wrong? There's nothing wrong with that picture. It works, right?
No,
So what happens next?
It's fine, but what happens next is we start to discover things, physicists start to discover things like electricity and magnetism, and in putting together the rules that those phenomena obey, Michael Faraday in the 1800s works out that it would be helpful if we thought of the influence of electricity and magnetism as something sort of spread out through space and time.
Right. Well, that's not exactly true. And then Faraday had a whole gear theory. So, blah, blah, blah. He had a lot of ideas that weren't accurate and true. But the real key to the concept, one of the keys, was time. Okay. And the fact that, Newton didn't know. He didn't have any way of knowing that light had a speed and all of this kind of stuff. And so it wasn't, late in Newton's life, I guess it's sort of, there's a line there somewhere where obviously it was deduced or inferred that there's some delay in how light travels. And likewise, there's a delay in how gravity travels. And likewise, there's a delay in how magnetism travels. So all of the things move at the same speed. And you could say, if fields were full of something called force, you could say it's the speed of force. And so you're just saying that everything communicates with everything else based on some little stuff, invisible stuff, that basically takes time to get from one place to another. And so now all you're trying to figure out, the Maxwellian question, is just understanding why there's this difference between a proton and an electron. So I figured I would go into some of just understanding this. It's all just pressure, and it's obviously always, in my opinion, obviously could be understood as everything's just reflecting a piece of the universe back at everything else. So that's what's communicating. Nothing intends to communicate. I don't intend to communicate. Okay. See, I'm sending photons to you, by doing that, right? I'm changing the universe you're seeing. By doing this, just by moving my hand and doing that, I'm changing, you're seeing many more photons come flying at you, a whole bunch of things change because I changed something. And so I'm just reflecting to you. None of it, I didn't produce any of that energy or that light. It's all just reflecting. So I'm changing what you're seeing because I'm changing what's reflecting off of me. And that's how everything is interacting with everything, is based on what it's reflecting. And it can be understood that simply, that there's an object in the universe. The universe, has energy in it. So yes, the universe doesn't have a cell phone, and the universe doesn't have, radio towers, and the universe doesn't have flashlights. But the point is let's just say the lights are on in the universe. That is, it's full of energy, stuff moving. And the fact is that, did I turn the camera on? No. Yeah, gotta do that. There we go. Did I move it? No. But there's a nice big round image of it. And all that's really taking place is this thing's position in the universe is known by something over here, because the fact is it's going to reflect energy. This stuff is going to reflect off of this thing and end up coming down here, and then this thing will be able to just see it. They can just see this thing's position because it's going to reflect energy to it. And now it's going to see if there's a light source. Now, if there's no light source, there's still energy, but it's not the same form we can see. It's not the kind we can detect easily. But you could still say that, if you have the right instruments, you can detect radio waves bouncing off of it, or you could detect some other kind of energy that's bouncing off of it. So it's all dependent on us being able to see the energy. Now, we can't see gravity. We don't have anything called a gravity eye, a gravity detector. What do I do with the damn... I gotta go jump on. Use this one. And so... So we're dependent on only certain kinds of radiation have to hit this thing. So, and obviously we're talking about radiation at a frequency. We can identify radiation at a frequency. And so if radiation comes off some source at a frequency and it bounces off of this, we can, well, I should bounce it off the right one, the frequency. We can detect the frequency. So we can't see just any kind of energy that bounces off. And we have to see, you know, and bouncing off means it can bounce off at all kinds of different rates, right? It can bounce right off right away, or it can go inside and then come out later, okay? And the simple argument I've made to explain gravity is that, you know, this force field, this field of energy that's always hitting everything, okay, the fact is it's moving the electrons and the protons. They're being moved from different positions all the time. They're jiggling in their position. They get hit by a bit from this direction, they move a little bit that way, and then they get hit from this direction, they move a little bit that way, and they're constantly moving. And by constantly moving, they move, the electrons and the protons move a little slower, okay, than the speed of light, the speed of the force. So when a force bit hits matter, so the force goes c, and then when it hits a little piece of an electron, it goes a little bit less than c. And then when the counter force shows up and the force is released, it goes back to going the speed of light. But it loses a little bit of energy changing the position of matter. And obviously if you're just jiggling it, you're not making a substantial change in the matter. It's always sort of in the same area. So all of this is energy that's sort of wasted. I mean, you consumed energy to go over here, and then you move back over here, and then you move back over here. It all doesn't add up to anything. So in a sense, that's in a sense, energy isn't conserved under that strict definition, because you've, over a period of time, you've done something to slow the force down, and you haven't changed the universe any. You went from point A, you went to point B, then you went back to point A. The universe didn't change, but you did use up energy to go from point A to point B. So the obvious point would be then is that something like the Earth, because it has a bunch of little bits in it jiggling, going from point A to point B, back and forth, it's constantly using up a little bit of speed of this stuff that was on the outside, the stuff going the speed of light. It doesn't quite go the speed of light inside of here. It goes a little bit less than the speed of light. And so therefore it radiates a little less energy than went in. And that's gravity. That means that when you're sitting here, the regular universe is hitting you with c energy, you know, speed of light energy, and the Earth is only reflecting a little less than that. And therefore there's an obvious imbalance, and you fall into that imbalance. Now the simple truth is again, Newton's theory of gravity could be understood as him saying, okay, there's a velocity this way, and all I'm going to do is apply another force this way, and that's going to cause a constantly create a circle. Now there's no real circle. There's velocity this way, and there's velocity this way, momentum, and all I'm doing is combining the two, so there's no true circle. There's just a constant reevaluating of what your vector is going to be based on the two things that are hitting you. A wind blows this way, and then a wind blows this way, and you go some combination of those two, and so you're constantly recalculating your momentum, and your momentum just keeps changing, and the change is eaten up by the circle, and so it doesn't add up to a change. All right, so that's so simple. So what electromagnetism and well, I guess we'll just say it that way, and charge, and they're all the same thing. It's all the same mechanism. And the point is that there's obviously this distinction between electrons and protons, this difference, that you can have the same field, okay, and you have these two elements, this minus thing and the plus thing, and it's obviously some feature where the same field is interacting with these things, and one of the objects in the same field doesn't do anything, and the other object says, I'm moving this way. All right, that's what we can say for certain, is that one element. There has to be an inverseness. So one field, same field, they have two different reactions. I mean, this one, in fact, will move this way. All right. So you have two different interactions in the same exact field. And so it could be understood that, well, maybe both of them are reacting to a field that has two elements in it, okay, that is causing this effect, and that when it's biased and has more of one element, then one thing interacts. So this is where it gets simple. Okay, I mean 2 plus 2 plus 2 physics. So all you have to understand is that energy, that gravity, is really made out of two kinds of force. Okay, a force. Whoops, that's not in the picture. Yeah. All right. Is that in the? Well, it's barely in the picture, so I'll make them this way. What the hell? Okay. So the field that makes gravity is really made out of two forces, okay? A force that pushes protons and a force that pushes electrons. And all you're seeing when electrons and protons are interacting with each other is the difference in the sense. So I have two kinds of energy in the universe, okay? We could call it plus and minus, or north and south. And I have two kinds of matter. Plus and minus are south and north. You know, this would be the north constituent, and this would be the south constituent. And that's all you need now. Now you can create the two inverse reactions, because I can just change the field to yellow and push the electron, or I can change the field to blue and push the proton. So the simple point would be is that all I have to do to make this work is just have a simple rule that when negative force hits negative object, that is, blue hits blue, it moves the blue object. When yellow hits blue, get rid of this. Well, I'll just make it shorter. You can keep it just to understand. You know, okay, so and then when yellow hits blue, nothing happens. This object doesn't move, and the yellow force just changes what dimension it leaves in. It leaves in one of the perpendicular dimensions. So one of them causes matter to move, the other one doesn't cause the matter to move. That is, it's benign. So obviously if I have the same number, if I have the same amount of energy in the universe, that is the same number of blues and the same number of yellows, okay, and then I find some way to segregate them, or you know, they're all mixed up, and I find some way to segregate them, and that is I have blues going one way, you know, yellows going more, a couple more yellows going this way, and a couple more blues going this way. You could understand that that difference is going to make a huge difference, in the sense that the electron will go this way and the proton will go that way. So all I have to do is change the relationship in any one area of the universe, any small area of the universe. All I have to do is create a bisection of that field. All I have to do is change so it's not balanced. See, if I have the same amount of yellow and the same amount of blue hitting this, then it's just like, okay, it doesn't mean anything, right? So if I have two of both of those, and I hit a proton with two of those, and I hit the electron with two of those, they're going to both do the same thing, which is only recognize the two that are hitting it. Well, that's probably a better way of saying that. And that's all they're going to see. They're not going to see the other force, but they're both going to be moved the same amount, because this one will react to the yellow, this one will react to the blue. All right. So next point in the theory is, all right, so a field is just a way of describing the fact that the universe is full of the energy. And again, we already have every intuitive reason, every logical reason to accept that the universe is densely packed with a bunch of this energy stuff, you know, these things moving. And again, we can understand that what is the energy that exists doesn't necessarily have anything to do with seeing something moving. Like, it doesn't, the only way to move in the universe isn't from here to here. The other way you can move in the universe is, yeah, you just go back and forth. No, well, that had no hope of being in the camera, so, all right. Gotta remember, draw higher, So I could just lower this, and then that should help me. Alright, so this is the top of the board. This is the bottom of the board, right? That's what I really should do, is make myself some references. Alright, so there's the only choice isn't just something moving this way, okay, and actually going someplace. The other choice is that something just moves from two positions and it just goes back and forth, back and forth, back and forth. And so, you know, motion, energy shouldn't be understood as you have to see something move to have energy. So the obvious comparison would be something like, you know, gravity or some other force, like tug of war. You could argue that when things are pulling, okay, but the flag isn't moving, it doesn't mean that no energy is involved. It just means you're not seeing it. Okay, you're not seeing an imbalance in the energy, but there's plenty of energy being exerted. These guys are pulling as hard as they can, and these guys are pulling as hard as they can. They're sweating. They're doing all this moaning. So there's a real event happening, but, you know, it's not obvious. Okay, so just a moment. Alright, should be back. Alright, so when they say field, and the obvious point would be field of what? The field is just a bunch of this energy that's in the universe. That's it. That's what the field is. It's just energy, energy, energy. And then I'm making this simple argument that there's more than one kind of energy, and there's more than one kind of object, and therefore there's these different reactions. So we said if I made an infinite amount of this stuff, just a bunch of it, okay, going in all kinds of directions, from every object's perspective, it would look like everything's just coming right for it. The only stuff it interacts with are the stuff heading right for it, so to speak. So everything would look like, in terms of how the universe is coming into it, like a sun radiating, you know, rays of light. That's how everything would look, both in terms of what comes in and what goes out. So you're sitting here as an object in space, and you're just interacting with this field, okay, of energy that's coming into you. And then everything else has to interact with a field of energy that radiates out of you. So if I put one object in the universe, oh, you couldn't see that. Yeah, a little sun. Can you see it over here? Yes. Okay, so a little sun. All right, that's how everything sees the universe, and that's how everything looks in the universe. It's just a little blob radiating energy, radiating this stuff. And the fact is depending on the stuff you put in the universe, it will radiate something differently. So, you know, if I had one object in the universe, we know that the pink stuff's going to reflect, and the blue stuff, you know, eventually, it's going to reflect. It's going to push the object will get pushed from the other side, and it'll reflect the energy. So eventually it's going to reflect what goes in, and it'll just be a little delay in when that reflection takes place. And when this other stuff comes in, it's going to leave in some other direction. Now, if there's nothing else in the universe, that's going to look totally even. Okay, purple is going to go in, that is red and blue mixed is going to go in, and you're going to get red and blue mixed out. Okay, but if I put two objects in the universe, then things get interesting, in the sense that what they do is create a kind of a dipole, you could argue, a kind of different kind of circumstance. So if I put two objects in the universe, now it matters which way energy comes in and which way it reflects, right? Because if all the blue goes out this end, okay, that comes in this way, and all the pink goes in, wrong, opposite colors, opposite. Okay, so the opposite colors come in, and if it all radiates out in one direction, right? Did it the wrong way again. Okay, it all radiates out in one direction. It goes this way. Okay, and then that comes out of this object this way. You could understand that you could end up with places in the universe, okay, where there's a real imbalance now in the field. So something looking at it, okay, would see something completely different. They wouldn't see purple anymore. They would see distinctively blue reflecting off one end and pink off of another end. And so depending on what their perspective is, looking at the magnet, for example, if we could actually see magnetism, you know, and you turn to the south end, you'd see red. and then I turn it to the blue end and you see blue in the north end. Then you could see that that's the simple function. And so now something else in the universe is going to react very different from these two sides. If I put an electron here, it's going to get reflected and it's going to move away strong. And if I put one over here, it's going to end up getting pushed by the blue energy, still hitting it from the outside of the universe, but it's not going to get hit by any blue going this way, so it's obviously going to move right into the proton. It's going to move into the red side. And so now you can understand the simple mechanics. So the field is a real thing. The field has real stuff in it. It's moving. The gravity, the energy from the Earth, what it's radiating, goes through space, travels to the moon, and applies its energy. It applies its the effect. And as I pointed out, you can sort of understand that for the Earth and the moon, that what the Earth is doing, the outside universe is hitting with a certain amount of energy from one side, okay? And again, it's red and blue, so it's hitting electrons and moving. It's moving electrons and protons equally. So if the Earth is sitting here and the moon is sitting here, what is the moon seeing? Well, when it looks at the Earth, a certain amount of energy is going in, but a little bit less is coming out. So again, the pressure that it would have hit it, this is the energy that would have hit it, and this is the energy hitting it from below, let's say, up from the universe. This energy is a little bit more than this energy, because this energy got consumed moving little tiny pieces of the Earth. It moved little tiny pieces of the Earth in this direction. Now it also moved little tiny pieces in this direction, but obviously the moon can't see that. Okay, the stuff moving away is invisible to it, so it isn't affected by that. It can only be affected by the change in the force coming down. So there's a little bit less here. This is a little less energy than was here. And this now is a little bit more energy hitting it from this other side. So the moon's going to get hit by more energy this way, then it's going to get hit this way, and that's gravity. So gravity is actually an absence of force. It's not the presence of force. Gravity isn't caused by adding force. It's caused because you subtracted a little tiny bit of energy by moving bits of the Earth. And the moon is doing the same thing by moving. It's clearly consuming energy, right? To move, it's got to consume energy. So it's consumed energy by moving towards the Earth and just by having matter that jiggles. All right, so it's making gravity, and as it moves towards the Earth, it makes even more. So because now that's an obvious increase in the amount of movement of the electrons and the protons. Something's always screwing up here. Yeah, so someone might be always screwing up here. Oh, that's not right either. Too much mirror, too much of the silver. All right. So I don't know if I need to go too much further into it. I'm just saying a field should be understood as being a field of something. The something is moving the speed of light. You already know it comes in these different forms. And all I'm saying is you want to explain the different forms, it's pretty easy to do. So you know that light, okay, is that stuff at a frequency. A little bit of force, a little bit of force, a little bit of force hits at a frequency. That we call light. I really do have to just draw on here where it's legal to draw. It's not even worth trying to save it. Anyway, so frequency is what makes light relevant. And then gravity, I would argue, is just the consumption of the force. That is, the force gets slowed down moving matter, okay? The less than c thing happens, and so it consumes a little bit of the energy of the force by moving matter. You slowed the runner down by making him carry a load, and that has a consequence in the universe. That is, the runner doesn't get as far down the track, and therefore can't have more interactions. So he has less interactions, the more he has to slow down and carry rocks. So that's a simple argument. So you explain light, all right, it's just frequency. and I can explain why frequency is important, but it's, you just know that that's the key factor of light, is wavelength. For gravity, it's just a consumption of energy in the universe, so it's consuming a little bit of energy by forcing runners to run slower, by giving them rocks to carry. And then the whole electric and magnetic thing can be simply understood as the force, okay, comes in purple into some system, and it comes out, okay, segregated. It comes out, more blue going one way and more red going another way. And as soon as I do that, I'm going to create the two different fields for a charge to recognize. The charge will see the two different fields and be affected in the opposite way by the two different fields. And again, the objects are always communicating with each other. You can sort of understand that if I have two protons, that the energy can get, the red energy would get trapped in between them, and that would cause the strong force, or the strong force of repulsion between these objects, and that the closer I bring them, the more they repel, just like two ping pong paddles and a ball bouncing between them. So anyway, I'm just saying all of the forces, all the fields, everything called a field can be understood as just some manifestation of momentum. And the fact is all I have to do is give the momentum two different colors, and I can explain why there's two different, why the electron and the proton are opposite in their function and reaction. So it's just about segregating the force, that is, separating the colors, taking the purple and making it red and blue. It's just about a frequency for the blue force that moves electrons. So the electromagnetic spectrum is in the blue force, because they're on the outside of the atoms. And then the other one is just the fact that you lose some momentum regardless of what force you're applying, when the force has to actually move a piece of matter. And with those simple mechanisms, you explain all these field stuff. That's the unified field theory. That's the simple explanation. That's the one that works. You don't need any of this ESP crap. You don't need any entanglement. You don't need any of the nonsense. So we'll play a little more of this. They don't really say much, so it's a little disappointing, but there probably is something worthy of comment.
Okay, but when we teach electromagnetism, we start with something like Coulomb's law, and Coulomb's law says if you have a pair of charges, similar to the way that
So Coulomb's law is a good example in the sense that it's doing the sun radiating thing. Charges are understood by just drawing radiating lines. Okay? Same amount of radiation is coming off of them, and the two charges are radiating the opposite thing. So he doesn't draw them as two colors with two different kinds of radiation, but if you did understand it that way, you could understand that all you're doing is calculating how much purple there is. So I can take a blue line from an electron, and I can take a red line from a proton, and I connect them to some location, and it'll just be dependent on how long the line is. If the line is short, then it's more blue. If it's a short blue line and a long red line, then you'll know it's more blue purple. Then if it's the other way around, it would be more red purple, so more violet. So you're just changing the density of the colors, and that'll tell you exactly what the field is there. Is it more blue or is it more red? And if the lines are exactly the same, then you'd say, yeah, it's purple, it's even. An electron moves just as much as a proton, which is not at all.
Instead, if you have a pair of masses, you can calculate the force of one charge on the other charge and vice versa, and then you can use F equals ma, Newton's laws of motion, to calculate what happens to the charges. And you actually have a similar thing for...
So all of that only works if you have a system where the changes over time are circular. They consume each other, so there's no permanent changes. But if any system that has permanent changes, like it's not just doing the wobbling thing, that theory won't work without you understanding that the whole force thing is applied over time. It takes time for the blue force to get to the pink thing. It takes time for the red thing to send its force to the blue thing. And the same is true for gravity and everything else. It takes time for the force to get there, and therefore like I said, the sun could blow up. I didn't say it, but obviously the sun could blow up in an instant, and we wouldn't know about it for 8 minutes.
Magnetism, right? So magnetism you get created by a current.
Yep.
So if you have a chunk of current
Yep.
and a charge, then there is a relationship between the current and the charge that tells.
So again, we know this current argument is true of electromagnetism, and this is the funny part, is they think that's the elemental magnetism, when they know it's not the elemental magnetism. We know that the regular magnet, okay, the earth magnet, is creating magnetism, and there's every reason to understand that it's not doing it because of some nuclear power it has. Like, it's not decaying, it's not churning or using energy to create the phenomenon. Simply put, all it's doing is filtering. All it's doing is something very simple. It's just saying, if a a red force hits one end, I'm going to reflect it. If the blue force hits the other end, I'm going to reflect it, and I'll just transmit it if it's the other color. And so it's not using any energy. It's just filtering the energy of the universe. It's just a filter. So it applies no new energy to the system. It just changes the profile of the energy in the system. So there's the same amount of light, same amount of blue, same amount of red. It's just taken the blue and sent it one way and the red sent another way. That's it. Now, if they understood a magnet like that, instead of understanding it as, well, when you put electricity through a wire, what you do is change the shape of the atoms, and by changing the shape of the atoms, you polarize them. That is, you turn them into little magnets. So an electromagnet is turning atoms into magnets, okay? It's not the natural magnet. But it's still doing the same thing, is that once you change the shape of the atom, you don't have to add extra energy. The atom is already being a filter, so it's just filtering. So you're just making more atoms into little magnets, and by making them into little magnets, they do the filtering thing like a magnet, and because they're all pointed in the same direction as magnets, they will look like a big magnet. Not complicated, really.
The force on the charge, and then you can calculate how the force behaves, how the charge behaves because of that force.
So the charge doesn't make the magnet. The dipole makes the magnet. You have to have both sides of the charge, or you've got no magnet. So again, you have to have the dipole, and it's just the atom's arrangement that makes it into a magnet. But it doesn't use any energy. You can make a magnet without electricity, is the simple argument. So obviously, it isn't about moving a charge. It's just about dipoles. And when you move charges in atoms, that is, when you move the electrons, you change the shape of the atoms. And by changing their shape, you turn them into magnets for a little tiny period of time. While the electricity is flowing, while the electrons are being moved, the atoms become polarized.
Difference between electricity, magnetism, and gravity. When you do this thing for gravity, the force on this particle over here with mass depends on where this particle with mass is right now. And so to keep track...
So again, that's not gravity as we know it, right? That's only for Newton. Newton didn't know the difference. But Newton wasn't... it wasn't like Newton was saying it's instantaneous. He didn't know the answer, and he made that clear. So again, this idea that Newton was seeing it that way, he wasn't seeing it that way. He just didn't know which way it was.
Of everything, you just need to know where everything is now and how it's moving. With, say, electricity and magnetism, if I've got a charge here and I've got another charge...
So this was all revealed in the fact that obviously the Newton's math worked better when you applied a speed to light and then applied the same argument to gravity. The gravity moves the same speed, the math worked even better. So that's the real point. So the point is, this Newton's math was close enough because we couldn't see the difference on these huge giant scales. The amount of difference in the time doesn't make any difference to a huge difference. But clearly the little errors that did exist in Newton were cleaned up by recognizing that when you were saying Venus was in a certain position, your observation was technically a little bit off. Because it wasn't actually in that position at that exact time. It was in a different position because you hadn't seen the photons from the new position yet.
Charge here, and I move this charge. This one doesn't move straight away. It reacts a bit later.
And again, it's not a bit later, it's always at the speed of light. So why don't they just concede the point? There's obviously all the communicating elements in the universe are moving the speed of light. It takes time for one thing to see that something else has changed its position. And obviously the closer things are, the tiny scale, it's almost like this time thing. Well, you can't say it doesn't make as much difference because things are moving so tiny a distance at such high a frequency that obviously it does make a difference. And that's why there's lag in inductors. Inductors and different things, there's a huge amount of lag because they can't know something changed until the field change gets to them, until the energy gets to them.
So the way that we sort of fill that out is it's reacting to where the other charge was a certain time ago. And so in some sense that we're going to have to put together somehow, the information about I moved over here takes some time to get over to this other charge. Now, do we want to talk about information? How do we want to flesh all of that out? What Faraday thought was, okay, let's imagine there's a...
So again, there's no point in calling it information. That's just getting it wrong. I mean, it's a real mechanical thing. The field is stuff. The stuff travels a distance. So it's like the soldier has to walk to your house, knock on the door, and then stab you in the eye. I mean, it's a process. It takes time. It doesn't happen instantaneously. So the universe is made of this momentum stuff, this little stuff, this invisible stuff, generally speaking. We don't see the photon, right? We don't see the little bits in the photon. We don't see the stuff at a frequency. We see the effect of the stuff at a frequency.
Field here, and when I move this charge, it changes the field, and the field sort of ripples a bit, and those ripples take some time to get over to the other charge.
So there's no field that you need to ripple, all right? It's just this simple fact that you change the field by being a dipole, for example, and now you're reflecting blue light at one end and red light at the other end, and you're sending that message. And that's what all the Maxwell's equations indicate. A bunch of straight line vectors at the speed of light.
And this charge here responds not directly to this charge, the second charge. What it's responding to is the field that was created by this charge, and which takes a bit of time to react when you move it around. And so
So again, a bit of time. We know that time is always the same time. It's the speed of light. And the only time it changes is when you put a bunch of matter in the way, and now you have a medium of the matter, the obstacle course that the force has to travel through.
There's a sense in which we're just sort of, we're trying to take account of the fact that these things I don't just have to keep track of where everything is now, I have to keep track of where it kind of was a while ago. And that seems what the field is doing.
But when we say field, what do we actually mean? I mean, but not the philosophical, right? So what we're really saying is that we have a charge. Mm-hmm. It creates something we call an electric field. Mm-hmm.
Right. So again, I'll just argue the simple argument. You're just sitting here in the universe, and a bunch of energy hits you, and then you don't do anything with it, really. Okay? I mean, some of it's moving your atoms, no doubt about it. But the net effect is that you're excreting just as much that went into you. You're at equilibrium, in a sense, with the universe. And your gravity is this little tiny amount of force change because you had to move the little atoms and the jiggle the electrons and the protons, and they're moving, and that consumes a little bit of energy, and so that's why you're excreting a little bit less than came into you. But everything is just doing that. Everything's just reflecting an image, okay, that's going to be made out of stuff moving the speed of light. So just like light, there's an image of the cell phone radiation bouncing off of me, or some of it going through me. The radio waves, the radio photons, the cosmic rays, all the energy that's hitting me is either going to go through me, through my atoms, be transmitted, I'll be transparent to it, and it'll be conveyed through me, and be re-excreted. It'll be converted into heat, and the heat will be converted back into, for example, infrared photons. So I'm just going to re-radiate whatever came into me. And the simple argument is gravity is created by the tiny bit of change created by the little bit of slowness that the force ends up doing because it has to move the heavy matter. And then all the other reflections are going to be based on how many electrons and protons and what arrangement they are. If they're in a particular arrangement, they're all going one way, then I'm going to, parts of me are going to look blue and parts of me are going to look pink and all that kind of stuff. So I'll change from radiating purple to radiating blue or radiating red. But the bottom line is I'm always going to be, in a sense, I can't change the amount that came in. So if purple came in, I have to make the same amount of blue and the same amount of red somewhere. You can't destroy any of that force stuff. You can only slow it down. So that's one of the principles here. That little stuff never dies. It never ceases to be doing something, going somewhere. And it's the only thing you can do is slow it down a little bit by making it carry a matter boulder for a little tiny period of time.
And that electric field is everywhere.
Yeah,
So fills all of space, and it has a particular value at every single point. And
So again, the idea would be is obviously every single point won't have a piece of momentum in it. Okay, so like when I send light at a frequency, there's obviously stuff at one point, and then there's a distance where there isn't any stuff, and then there's more, stuff again. And then there's no stuff, and then there's stuff again. So I've obviously created places in the universe where there isn't any blue energy. It's just not there. That's what I've done. I've changed it. I've changed the proportions and where it is just by doing this change of direction thing that the little electrons and protons are doing. So they keep changing the direction something's moving, the dimension it's in, and it can shove more pink in one dimension and more blue in another dimension. And so you get these disproportions that can exist. But there's not some location, and every location in space actually has a piece of momentum in it. But from your perspective, that's exactly how it'll look, because you can't see all the little spots of space. So, generally speaking, yes, it's true. You can look at it that way, but it's really not true. That overall, as an average, there's always going to be energy in every hunk of space traveling through that hunk of space, but the amount of it can vary.
because the electric field is a particular kind of field known as a vector field, not only does it have a value at every point, it has a direction. Okay, so
the value just means where it is, okay, and the amount of potential it has already been quantized. So at least they got that part right in terms of understanding. All it can have is a momentum. It can't, in a direction. It really can't change how much momentum. You can't be a little bit or a big clump. There's no big or little clumps. There's just a pointing, direction. So whenever the force does exist, it's only one little discrete piece of force, and it's only got a direction. But they're just missing the part where, no, there's lots of places in the universe where there's no force bit. There is no momentum.
We say that this charge fills the entire universe with a field that has a value and a direction at every point, as does every other charge.
So again, this is just an answer, a model they made up. There's no reason for you to believe that model is complete or sufficient, or it deals with any of these inverse relationships, because it doesn't. So, and again, the only modification I'm making to it is I'm saying, no, the momentum bits are real. They move the speed of light. They fill space. They're all over the place. There's zillions and gazillions of them all the time, flying into you all the time. And you're radiating them back, and that's exactly what we see. Is we see a kind of thermal equilibrium with a tiny deficit created by the fact that, again, if a piece of force has to interact with a piece of matter, the piece of force will be delayed in its progress. It won't get to the next town when it's supposed to because it got slowed down.
And as you move these charges around, that changes these fields. And as you mentioned, there's a time delay in how the fields respond. There's a ripple that travels out.
So there's no ripples. It's you don't need any mediums here. You just need clumps of momentum that are small, and bigger things called matter that the clumps of momentum have to push. And that's all you need to answer all the questions.
And as you move charges around in that field, that also produces another field called the magnetic field. Right? So
there's no such thing as two separate fields. There's only one field. It's the charge field, if you want to call it that. The electron is doing something different to the two forces. Okay, and it's exactly the opposite of what the proton is doing to the two forces. So it's just this simple point that, if the electron is alone in space, you won't be able to see the difference between a force going this way and it went out that way, because it's still going to be the same amount from all directions, because just as many that went in this way are going to go that way as went in this way and came out that way. So it's all going to look the same until I put another charge in the universe. Then you're going to see the difference. Then those right turns matter. They don't matter if there's nothing for the force to hit. But as soon as there's something for it to hit, it's going to be relevant, because it's going to have to do with those reflections. But anyway, yeah, so there's no more than one field. There's just blue and red and purple. And understanding it in that sense, you can understand anything. Gravity is a purple force. Photons, visible light, is a blue force at a frequency. And charge is just that red and blue force and those two inverse reactions. Moving, but because of the force hits you, and not moving when the force hits you. That's all you need.
Yet that each individual charge produces this thing that fills all of space, and other charges are reacting to the field in their vicinity.
Mm-hmm. Exactly. They're reacting to the fact that that other charge is sending me more blue than red. That's all it needs.
So maybe
it's sending the guy on the other side of the universe more red than blue, right? It sends me more blue than red. Then it means it's somewhere else it's sending more red than blue. So it just matters on which side you're on. And that's the nature of polarity.
a good way to think about it is just mathematically. When I boil it down to what do I need to do mathematically, in Newton's universe, what you need is the positions of all of your particles and their masses and their velocities. Okay, so what you end up with a mathematical object, which is
all your particles. See, that doesn't even say anything, because obviously Newton is saying yes, the moon is a particle, the Earth's a particle. They have their momentum, but he's obviously got to account for some new force that's applying a new momentum, and he didn't know what it was. But obviously, particles explains it.
For each particle in the universe, I just have a list, a list of all the particles, okay? And for each one, I just have where it is, how fast it's going, and how much it weighs, its mass. When you get to this field idea, you need a different kind of mathematical object. You don't need, okay, where is particle 1 and I get X, Y, and Z. You need something where I put in a location.
Okay, so you don't need any of that if you just understood that, oh, wait a minute, the little particles, the field particles, actually do lose energy, a little tiny bit of it, when they have to move a piece of matter. So, like I said, it just explains perfectly why there's gravity. Because the force on the outside isn't slowed down by pushing matter, the force on the inside is. There, you're done.
In the universe and a time, an X, Y, and Z, and a T. I've got to put that into a mathematical function, and out the other side has got to come the value of the field. Now, depending on how many numbers come out, depends what type of field it is.
Right, so let's understand, when they put these numbers in, they're always putting them in some Gaussian or Maxwellian sense, in the sense of understanding them as just being vectors. Okay, and vectors that have an inverse effect on electrons and protons. So those assumptions exist. That's how they understand the force they create moving the speed of light, but they haven't identified why the different exists, and that's the key point. Okay, they haven't explained why the electron has an inverse reaction, because they don't understand that the force is inverse, that there are two kinds of force to match the two kinds of matter. That simple thing fixes it all. It makes it all much simpler and easier to understand.
You're talking about a vector field, so 3 numbers come out, a direction and a length. And so mathematically, that's a sort of a big change. The fundamental thing, mathematical thing we use to describe the universe changed from Newton to Faraday to these fields. And so the question...
No, so the only thing that changed from Newton was understanding the speed. That's the only difference that matters. And again, as I've pointed out, Einstein's Newton not accounting, nowhere in Newton's math did he account for the sun processing. That is, you didn't see the sun process, so you don't think the sun's processing. But the sun is a massive object, huge, and it's got different densities. The center has got a different density than the outside, like all planets even. That's just because of gravity. And so what you see on the outside doesn't necessarily have anything to do with what's happening on the inside. The outside is detached. It takes time for any influence on the inside to get to the outside, and by the time it gets there, it's already been averaged out. So the center of the sun, its actual center of gravity, all it has to do is precess a little tiny bit. Just has to just do this, a little tiny bit, go a little bit around, and that explains Mercury's precession. So it's that simple. That's simple an explanation for the only thing that's making a difference. So there's nothing else that's changing anything. The sun is obviously precessing because the planets that are affecting it gravitationally are all in different positions. So obviously there wouldn't be any total perfect consistency. They're all in ellipses. They're all moving inconsistently, creating an inconsistent gravitational influence. So obviously the sun would precess.
The question now is, okay, we've done all of this, we've got all this apparatus that you said. Is it just a calculating apparatus?
Yes, exactly. That's all it is, and it's a generalization, and it's not perfectly accurate, and it doesn't work in all circumstances, and that's why they end up inventing dark matter and all kinds of other stuff, is because it doesn't work, and they should just recognize that their model is broken. And if they recognize that, then they'll spend a little tiny bit of time, and maybe they can figure this simple thing out. The forces are all the same force. Once you go into the physics saying, that's what I did, okay? Once I said, I thought of photons. I said, photons have to be particles. And then I said, well, what if gravity's particles? So then what if it's the same particle? Can I make gravity do the same? Can I tie the two together in some way where I can combine these things? And then I got to magnetism, and that was the spooky bit. You know, just like, oh, no, none of this swirly stuff works. I can't make anything. I can't make it matter whether something's spinning left or spinning right and all that. Those things don't make the difference. So I have to give it. And I'm just saying that's the process, though. They'll get you to this simple understanding that all I have to do is create two forces to match the two charges. Then I can have the inverse reaction, and I'm done. Everything else falls into place. I mean, gravity doesn't just fall into place. You still have to understand that, oh, wait a minute, moving matter isn't free. You can't move matter in the universe for free. It consumes a little bit of the force's energy. While it's moving the matter, it's not moving the speed of light anymore, and therefore, while it's carrying the matter, let's say, it's not running as fast on the track, and it won't make as many, it won't be able to go as many rounds the track in the same amount of time, and that's the definition of energy. You obviously have less energy if you made less rounds the track. So that's part of your momentum is your velocity, and velocity is about how much distance did you cover. And if you cover less distance, and photons cover less distance when they're moving electrons, then you have less momentum by definition. And the universe has less energy in it by definition. Alright, that's probably enough of a video. They really don't get anywhere here. They just have this blah blah blah. I could just jump ahead a little bit and say it just doesn't go anywhere.
That I'm not a big fan of saying that fields are real.
Okay.
In the sense that, yes, it makes you feel comfortable because you can talk about the conservation of energy, but for many people, conservation of energy is a comfort blanket more than anything else, right?
Well, conservation of energy is really just saying the force bits never stop. Right? So that part's true. There's no destroying of the energy. You never have a circumstance where the photon crashes and there's no energy impact. Nothing else changes in the universe ever again. You never kill one. You never kill the energy. And the only the only thing you're adding to that qualification that you can never destroy energy is, you can slow it down a little bit. So you can take a little bit of its momentum out of it. So yes, you can do that. But the slowdown does have a byproduct, which is the matter moves. But again, if I move a piece of matter from point A to point B and I just keep moving it back and forth, I'm not really changing the universe in any substantial way, so that energy is essentially lost. If I return to my original position, whatever I did, you could argue was just waste.
It's an accounting tool.
Right.
Okay. And in fact, when we look at various aspects of physics, you invent.
So they're just saying it's an accounting tool. They're just saying, again, we're not going to give this thing any reality. The field isn't real. There's not real soldiers that knock on your door and stick you in the eye. I mean, it's just stupid. The particles clearly are being completely controlled by the force. Matter doesn't do anything till a bit of force tells it what to do. It has no will of its own. It has no function of its own. It's completely a slave. Electrons and protons are a slave to the field around them. They will do exactly what that field tells them to do. The end.
Things to ensure you can do this accounting tool. So you talk about energy going from one place to another place, and it's always in something, but energy is one of those slippy sort of...
So yes, energy is a slippy concept in the sense that we're measuring energy based on where there's an imbalance in energy. So that's what we say energy exists. So we only see things where the change happens. We don't see the energy when it's equilibrium. And every bit of equilibrium is always, it's like the tug of war. The truth is these guys do push this way. They do move stuff that way. And these guys do move stuff that way. It's just that they're doing it at different times. The matter is actually going both directions. It's actually both forces are working. Just as right now, gravity is pushing you down. And you can feel the earth is constantly pushing you back up, okay? It doesn't give up. It doesn't push you back up once and say, there, I'm done. I did my job. No, it's constantly pushing you back up. So obviously the gravity is constantly pushing you down. So little bits inside of you at any one moment are going down, and little bits inside of you are going up. And it's happening all the time. It's just that they don't go up very far and they don't go down very far. But they're going up and down constantly.
Concepts in that you can't really put your finger on what it is, but you're happy that it's conserved. And as we've spoken about previously, it's not conserved necessarily.
Yeah, that's one of the, I'll put the link up there. Energy's not conserved in cosmology, which is a real...
But why does it bother you? It only bothers you because when you were in high school it was drummed into...
So they're not really talking about gravitational energy. They're talking about the expansion energy, which is a pile of crap. Again, the whole expansion theory is based on their misunderstanding of redshift. So, it's just another cascade of error on top of error on top of error on top of error, which is where we started with this silly lensing theory that makes absolutely no sense because the lens is a theoretical monstrosity. It has no coherent rules that it's obeying. So anyway, enough of a video, and we'll just endeavor to persevere and such, and so forth and whatnot. Again, I can only reason with you, and I'm telling you that you could be on the ground floor of getting it right, or you could be on the ground floor of being another belligerent asshole defending religion. So you can either have history say, oh, another religious fucktard who just sat there and devotedly defended absolute nonsense. Or you could be one of the people that jumped on the right boat and said, hey, yeah, I get it. It really can be so simple. And we really don't need all this fucktarded wooey crap. We don't need Jesus and the Holy Ghost and God and all this other crap to understand how the fuck we got here. Well, you don't need all their crap to understand how the universe works.